And we come to the last talk. Is this remote or is it? It's remote. So that is about the non-perturbative jet dispersion in hot QCD. Oh, you share already. Okay, go ahead. I give you a 5 minutes warning.
Yes. Hello. So, okay. Do you hear me? Great. So initially I wanted to be there, of course, in person, but I mean, something got in between, and now I'm doing it remotely. And in this talk, I want to talk about some recent developments on.
But at the moment, we don't see anything.
Ah, okay. Give me a second. Let me see if I can do this. Does this work?
No, not yet.
Okay, then I'll try again.
Now it's better. Yes, make full screen and then it's perfect.
Okay. Sorry. Does that work?
Yes. Yes.
Okay, great.
Thank you.
And it changes, right? Does it change to motivation when I do that? Okay. So I wanted to talk about the recent contribution to non-perturbative jet dispersion. And it's again also in of course in alignment to some of the previous talks where we have seen that lattice results and also perturbation theory should somewhat work together to deliver, of course, the correct and most precise results for some of the especially transport coefficients in the quark-gluon plasma. And here in what I'm going to talk about is the so-called asymptotic mass, which is next to the transverse collision kernel, one of the more relevant quantities that go into into further studies of transport coefficients of the quark-gluon plasma. And what's the motivation here, or rather, the question in this talk is rather what can we learn from the lattice about, for example, the asymptotic mass or about jets in specific. And in order to do that, we can have a look at heavy ion collisions, and the usual picture here is that in any of these heavy ion colliders, you have some heavy ions that get smashed together, and what comes out at the end of the day is this kind of transient, very short-lived quark-gluon plasma, and of course we want to probe that. And in order to probe that, there's multiple ways, and one way is hard probes, as we've heard already today.
Hello, you change the slide, but we do not see the change of the slide. You always be in the first page.
Oh, this is very strange. I'm sorry for that.
Now it's better, yes.
Yeah, okay, but I don't know why.
Let's just try.
Does that, okay, maybe I'm not going full screen. Let me give you a second.
Okay, then try this.
Maybe did that work? Does it change now? Or not? I'm changing slides at the moment. That's very strange.
Yes.
I can.
So now the slides are visible, but not full screen, but I think better leave it like this. And
yeah, okay.
Now it's full, yes.
Okay, I'll leave it like that. Maybe that works somehow. Okay. Okay, maybe you see it now. Okay. So interesting. Okay. Anyway, I'm gonna continue like that. So yeah, what I was saying is that so there are hard probes, and in order to probe the quark-gluon plasma, and one of these hard probes are, for example, jets. And when they go through the quark-gluon plasma, they can do all kinds of things. They can get broadened so that somehow they induce some medium induced radiation, so that there's some energy loss eventually, or they can quench, so to speak, eventually completely disappear at some point, or they can somewhat get displaced while they go through the quark-gluon plasma. And this kind of displacement is one of the things that I want to talk about, because then when this displacement happens, this will kind of act as an effective mass of the jet itself. So what we can see here is that, for example, what happens is that these jets can be very fast. So as for example, we've heard yesterday, if there's some kind of separation of time scales, for example, so that somehow if they're very fast, hard particles, they eventually live a different time scale, a different scale compared to the medium, which lives at a soft scale. And when there's this separation in scale, for example, then jets are of course fast enough to view the the medium itself as almost static. And this is one of the ideas that I will talk about later. In order to describe this, one can in fact use an effective theory that's in fact static. But what I want to motivate here is why we actually need non-perturbative contributions to some of these quantities that are of relevance for transport coefficients. And the reason for that is if you look, for example, here. Sorry, if you look, for example, here at this plot below here, we see this transverse collision kernel, which I said is one of the more relevant quantities, and as been discussed in this paper down here is that the leading order, for example, in a scenario where alpha strong is like 0.3, and that's some more relevant benchmark point for heavy ion collisions. So you can see that the leading order is down here, and that even the next to leading order, where I mean that leading order plus next to leading order, in fact is even at least of the same order as the leading order. So for this transverse collision kernel, you can already imagine that somehow that perturbation theory or the convergence of the series in fact is somewhat broken if one doesn't include something else that's needed, and in this case something else will a non-perturbative effects to this quantity. So let me just now introduce a little bit of these quantities, namely the collision kernel itself. As I've discussed, is this transverse collision kernel. So it's this it's a rate. So it means if a particle or a jet goes through the quark-gluon plasma, it's somewhat it will pick up some transverse momentum at some point, and at what rate that happens, that is described through this quantity here. And since the jet is so fast in this case, one usually goes into the light cone coordinates, so that here you can see that this transverse plane here to one of the light cone coordinates, and this quantity is usually described by a Wilson loop, and as I'll discuss later, this is also very well understood also from the lattice. But this is again, it's not the main quantity that I want to look at. It's rather this asymptotic mass. So as I said, if you have a jet that goes through the quark-gluon plasma, it will eventually gets all kinds of forward scattering. So it means it gets a kick in one direction during its the time in the quark-gluon plasma, and then at some later point it gets kicked back through medium effects, so that eventually its path direction is almost the same at the end of the day, but it picks up some kind of phase during that, and at the end of the day, this whole thing accumulates to give an overall effective mass to the hard particle. And in order to describe this, there are contributions that come from the gluonic sector and the fermionic sector of the theory. So at this order, and they both contribute to this asymptotic mass. But now the ideas and of course the question is, since we have seen that there are non-perturbative contributions already to the collision kernel, there are also non-perturbative effects to this quantity here, and the idea to really handle this has been put forward already here by Simon Carnot a couple of years ago, so that when you're close to the light cone, you can in fact describe for the system through the electrostatic high temperature effective theory. Well, it's the high temperature effective theory of QCD, and that captures in fact the infrared dynamics in a way that the UV of the theory is in the matching coefficients of the theory, and the infrared can be much easier simulated on a lattice. So one can in fact compute these quantities then on the lattice at the end of the day. So for that to happen, we can have a look at what is the effective theory that we use here, and as I said, it's electrostatic QCD, because in fact when you start from thermal QCD, which is 4+1 dimensions, you'll eventually integrate out the fast or the hard modes that live at a high energy scale, and the scale separation within thermal QCD is the separation between a hard, soft, and eventually ultra soft scale. So where the theory is weakly coupled at the hard scale, and so somewhat still weakly coupled at the soft scale, but definitely non-perturbative at the ultra soft scale. So all the modes that live down here are non-perturbative. So somehow when one can construct this succession of effective theories, eventually one ends up with a theory that completely encodes the infrared non-perturbative sector of the theory, while whatever has been perturbative is encoded in the matching coefficients, which is the usual construction of an EFT. But it's in fact just peculiar because in thermal field theory, of course, you have these Matsubara modes, and eventually the convenient thing at this soft scale is that the theory ends up being without any fermions, because in the Matsubara formalism, fermions are in fact they live kind of in the temporal direction. And once that is integrated out, you have a theory that's fully bosonic. So what happens is at the end of the day, you deal with a SU free theory at the end of the day in 3 dimensions. And what happens additionally is that the zero component of the gauge fields eventually become massive because the Lorentz symmetry gets broken because of the heat bath that has a distinct direction, and that the direction now doesn't protect anymore. Well, because there's a distinct direction, the A0 is not anymore protected from picking up actually thermally induced mass, which happens here. So this is the theory that one can use, and since it's a lot easier to simulate than full QCD on the lattice, that's usually the way to go when it's available. And here is the theory that we, for example, used in this collaboration. It's EQCD truncated at dimension 4 operators. So it has, as I said, it's SU free Young-Mills, but it has still done this these abelian scalars around that eventually have their self-couplings and masses. So that and this theory has been in fact very, very successful, especially to study high temperature thermodynamics and also dynamics of electroweak phase transition, as I've discussed before. But also is, of course, and that's why I'm using I'm leading up to this is that it's been used for soft light cone observables, and that's exactly what we're doing here. Like for example, with the asymptotic mass or the transverse collision kernel. Yeah. Okay. So what are these asymptotic masses that I've been talking about? And the question is, so how are they really defined? And for that we can have a look at this diagram here, which shows that so there's 2 different lines here, which are the poles of the propagator of the fermion, so the free solution here, and then the one which is the actual one when there is in fact interaction with the medium, and this free one eventually, this one which is the one with the actual dispersion relation, eventually approaches a different mass, of course, than the free one. And this has been found a long time ago, and this mass is of course different at very high momenta, and the asymptotic mass that in this context is the one that is the mass of a particle at very high momenta. And as we've seen before, there are different contributions to that asymptotic mass. For example, a fermionic contribution and a bosonic one. And here the fermionic one is in fact, well, it's a fermionic thing in at high temperature. So it means usually fermions are remain weakly coupled even at finite temperature. So there's not really necessarily a problem here in this computation, especially in terms of infrared sensitivity. But for the bosonic part, there's usually always problems because of the Matsubara zero modes, which eventually are the degrees of freedom of the effective theory. So here's to say that these 2 coefficients are in fact the leading coefficients if one computes this effective mass in an expansion of T over energy, which means that if of course in this case we are in EQCD, which is at a much lower scale than the energy, than the temperature. So which means that these leading order coefficients are in fact the only contributions here that are relevant at the next to leading order that we are computing the effect, the asymptotic mass. So okay, so one could potentially imagine there are more contributions if one comes close to the energy here, but I mean that's not the case in this computation. Okay, so this actual condensate of which contributes to the asymptotic mass is defined like this. So as I said, it's an insertion of two different force operators. As I said before, that when the particle gets these forward scatterings, it gets deviated twice, basically, once in one direction with force operator in one direction and once in the other direction. So one can imagine this is a correlator of two force insertions, and then since and then this correlator here has this covariant derivative in the denominator, so that somehow now if one writes this in position space, in fact it ends up being an integral over spatial separations, light-like spatial separations that are eventually integrated over, so that this one over the covariant derivative is eventually translated into this light-like Wilson line, which is in the direction of x plus here. So that this is of course the 4D condensate or correlator in this case, and then what we want, of course, is to have the same quantity in electrostatic QCD. And as I've said before, in electrostatic QCD, there's this breaking of Lorentz symmetry for the zero component of the gauge field. So what happens is that what used to be this just one correlator is now broken into to this electrostatic, and then this just magnetic contribution, and then this mixed contribution. This can in fact indeed happen. So that these are now the condensates that are in fact relevant to measure on the lattice. So as you see below here, there is this covariant derivative of this which used to be the zero component of the gauge fields, and then it's connected with this Wilson line just as above. But it has now three different contributions, which are individual contributions in electrostatic QCD. Yeah, and these are the things that we want from the lattice, and then we can take them, we can integrate them over, and then you get this contribution to this gluonic contribution to the asymptotic mass. Okay, so what's the strategy? And the strategy is usual that you start. What you want is, of course, the full QCD result. But what we have to do is we have to basically compute the QCD result in some way, and then we subtract from it the EQCD result, so that we have the UV contained here, and then eventually, so we basically subtract the infrared from the full result and add the infrared again in terms of the lattice result, and in this case we can in fact have the exact lattice result included. And in order to do, well, this has been done in this strategy for the transverse collision kernel before, so that's known, but here is now the first time for the asymptotic mass. So where this is now partially done, so that what we have done so far is then we have this lattice contribution, and we have this EQCD contribution, and the outstanding bit is then eventually this QCD full contribution, which I'll discuss later. What are the missing pieces to that contribution? But what I will discuss now are these last two pieces here, and how we actually get hold of them. So okay, so this is the EQCD side that's next to leading order of the asymptotic masks. And in order to look at that, we can now do this kind of strict perturbation theory expansion in the QCD coupling of the set G parameter condensate, and have a look what are the different contributions. And at leading order, so this is basically, so this is G squared here, this is G1, and this is G0. So at leading order, which means this first and second line, so at order G, you get these two contributions, and one can see now, for example, this T squared of 6 competes then in a potential relevant scenario for heavy ion collisions. It can compete with this term, in fact, so it can be of the same order. So one can already imagine that if one doesn't include non-perturbative effects here, that there is something going on that is not convergent in the series. And So that's already at leading order. So if one goes then to next to leading order, or G squared, which is what this computation is about, one can see that all different scales, namely the scale of temperature, which is temperature, and the scale of the medium, and of course this also scale of the non-perturbative effects are in fact all contributing to this set of G. So one has to really have the full contribution. So so here this side is done on the lattice. So this you can do in electrostatic QCD, and this you get from full QCD. But of course, all these contributions have to be taken into account. Right. Okay. So how do we in fact compute this parameter perturbatively? And for that, I can show you what are the contributions that go into it. So there is, so as I said, it's this force-force correlator, and it has now different contributions that are purely electrostatic or just purely magnetostatic on the endpoints, depending what is the correlator that you're looking at. And the leading order contribution is just this free solution here. It's basically a propagator that is Fourier transformed and then integrated along the Wilson line. So that's kind of the trivial solution. So as you see down here, it's just an example of how things usually go. Then you have this differentiation at the endpoints here, and then you have the actual propagator. And if this is carried out, it gives this contribution. It's kind of the leading contribution to this whole result. But then there's a whole chunk of other diagrams that come into play. Well, some of them are potentially trivial because of some symmetry considerations. There are definitely some diagrams that are relevant and harder to crack, but eventually all of them are, some of them are really relevant, and as we've done in the paper, we've computed them perturbatively and then eventually compared to the lattice. So that is the next step. Now that this is the perturbative computation, I can now show what is the lattice result. So it's the same thing, and here we have looked at 4 different combinations of temperature and numbers of.
There are 5 minutes left.
Yeah, perfect. Yeah, that's good. So 4 different combinations of temperature and a number of massless quark flavors, and what happens is that if we see now that there's, for example, at very high temperatures, and it's especially in the UV, so at small separations, of course, everything is supposed to be very well in agreement with the lattice. But of course, if you then go to lower energy, somehow, of course, the perturbative result will eventually not be as accurate anymore. So, but if one eventually subsidizes this result with the full QCD UV correct result, then the matching will be complete, and also this and also the UV side will fit very well. But what I'm saying is that there's very good agreement, which is of course great, because EQCD is well, here you see that, for example, the EE correlator and the BB correlator, and you can see that for this 100 GeV, this is very much correct, and reproduces, for example, the lattice very well here. And I can also show this now for example, for just the 100 GeV result at NF equals 5, and you can now see that the agreement between at next to leading order in perturbation theory compared to the leading order, which was just a free solution, of course, is now pushed to really small margins and close to the lattice result. Same here for the BB correlator, which is in fact remarkable, because one would in fact think that since this is a purely magnetostatic, magnetostatic contribution from the spatial part of the gauge sector, one would think that the non-perturbative effects are in fact largest for this one, but in fact it sits very well on top of the lattice, which is rather surprising, in fact. Okay, so let me then just conclude what we have done. So we've seen that the jet modifications are in fact prone to infrared sensitive effects, and they can be captured on the lattice, and especially here with electrostatic QCD. And the 2 key quantities are the transverse collision kernel and the asymptotic mass. And both of them have now been determined reliably in EQCD from the lattice. what remains now is what to do with what are the next steps for this asymptotic mass. And of course, as I said, we've done the EQCD computation by now, and the next step would be to do the full QCD computation, which requires some more considerations about the contributing operators and of course that would be that, and what else remains is now that we have, so once these quantities are under control, one can eventually use them as input as input for effective kinetic theories, and eventually, I don't know, give some very early ingredients for next to leading order transport. Okay, I think that's all I want to say. I hope you got a bit of an idea about what we've done in this computation, and yeah, thanks a lot.
Ask the questions, comments. I don't see here. The audience is no, also not in the internet. Okay, so let's thank all speakers of this afternoon again.